Hello, everyone. My name is Andrei Satarin. I'm going to be talking about the paper using lightweight formal methods to validate a key value storage node in Amazon S3. So let's start. The quick outline of the talk roughly follows the outline of the paper. So I'm going to be introducing the shard store, talking about what they actually validating in the storage system, what kind of properties they're looking for, different approaches and like different lenses they look at validating is, which is conformance checking, checking crash consistency, checking concurrent executions, some other properties they looked at in the system, and overall experience and lessons from that work. So introduction. S3 is like a key value object storage provided by Amazon S3, and the core of the S3 service are storage node servers, which basically are servers storing the actual data apart from like index and other control plane stuff. So the shard store is the new key value storage node, which is slowly, as at the time of the paper publication, is rolling out in production to replace the previous version. Overall, it's roughly 40,000 lines of code in Rust. It has concurrent implementation and responsible, like it should provide crash consistency properties, which complicates implementation. And like that's the goal of the kind of verifying that storage to check for those properties. So like the other goals is like basically API correctness. So like does API do whatever it's supposed to be doing? Do puts put, do gets return the results they should be returning. Crash consistency on disk is a big thing because system is responsible for that. And in the presence of crashes, we still want to have the data consistent and providing certain guarantees, correctness of the execution, because apart from API calls, there are also some background tasks executed concurrently, like for example, garbage collection. And the presence of those tasks should not invalidate any of the external guarantees this shard store provides. Also, the goal is kind of have a soundness correctness trade-off overall. So they're not targeting full formal verification of the system and like proving that it's absolutely correct. They're willing to accept weaker guarantees at the expense of like using more scalable methods. So like larger histories or larger scale systems or bigger APIs and things like that. So that's not like the idea is not to have like a fully verified storage. The idea is to have like some kind of trade-off between verifying correctness and having scalable way to verify it. In terms of the shard store, it's basically based on the large log structured merge tree. Data is stored in chunks. Chunks are stored in extents, and that's everything is stored on disk, obviously. So on the right, there is a picture from the paper itself. So because shard store writes to several extents at the time, at the moment, it basically means that like there are more than one write log, and that complicates crash consistency. And as I mentioned before, there is a garbage collection and other internal processes also complicates things. And the idea is to validate that. So what kind of properties there? Well, like what's their approach on validating this kind of system? So first of all, they look at the core properties, which is consistency and durability. Other things like performance and availability are all important, but not the focus of this work. They'll have different ways to validate those and like test for decent performance and availability. But the durability and consistency are the focus of this specific work. Other good properties to have in production is like absence of undefined behaviors, bound checking, like system not crashing, which are like desirable in operations, also there, but not like the main focus. So the other, one of the other goals is to have all the results of that outlive involvement of a formal method expert. So like basically they don't want to have a team of formal method experts supporting this forever. They want to like hand off it to the development team. So this is why they go in with a lightweight approach to formal methods, apart from other reasons I mentioned before. So what about durability, like the main thing? Basically, they view it through three different lenses, like split it in three different lenses, which is kind of like matrix 2x2 with sequential execution and concurrent execution, and the presence or absence of crashes. So this gives us like sequential crash-free execution covered in the section 4, or sequential execution with crashes, or concurrent and crash-free. Concurrent execution with crashes is specifically out of scope of that paper, so they don't talk about that, but all the others are covered. So I'm just gonna go through like sections as they go with the way they presented here. So the kind of thing they use a lot to check for those properties is a reference model, which is basically implementation of the same API as the short store provides in Rust, but way simplified. So it's like 1% of the size of the actual implementation. So it's like several orders of magnitude simpler because it does not care about certain other implementation details like failures, probably performance, other things. And this reference model also used as a mock in other tests, so like probably large scale tests where you don't need storage, but you don't want to run the whole system and you need something simpler to run in the test, not as large scale. That idea of using the reference model as a mock also helps to keep it up to date with implementation, because like if you implement a new API, basically you have to implement the new API in a mock in a reference model because you want to use it in some other test as a mock. So conformance checking, it's like the first step of providing durability, which is sequential execution with no crashes. For that, they basically use property-based testing, which is, in few words, is like applying random operations to the system and validating that it does not violate certain invariants. In this case, invariant is that like implementation refines the reference model, so it doesn't do anything the model doesn't do. And for some cases, to steer the whole thing into interesting states or interesting code, they do need to do argument bias. So kind of like not provide those operations uniformly randomly, but like some kind of bias them towards more interesting, more complicated operations to steer a system in interesting states. But they mentioned that only do this if there's like strong quantitative evidence for the benefit of that biasing, because otherwise you might bake certain assumptions you have of the implementation into the system, and that's kind of their idea of avoiding doing that. Do not bake into assumptions in the tests themselves, because that kind of will be self-validating the system, I guess, in a way, in a bad way. Also, they use code coverage to like look for those blind spots. Like if some code is not covered by property-based tests, you need to kind of figure out how to do that either through argument bias, some other ways. The model is also extended later with the failure injection, and there are certain failures they extend to, which is the fail stop crash covered in the crash consistency part. Disk IO errors, which basically the way they do it is relax the model to allow relaxed checking against the model. So like when this certain operation crashed, we basically have a certain we have the check which says like don't compare the crashed operations to the reference model. And some things like resource exhaustion is specifically out of scope for property-based testing, because it's kind of hard to extend the model to those accidental complexity things without making it more complicated than it should be. So crash consistency, which is, again, it's like sequential execution with presence of crashes. So the test system still controls every operation and still executes them sequentially, but there are some of the operations are basically crashes. And the crash consistency is the primary motivation for this effort, because like systems crash and you still want to provide durability guarantees in the presence of those crashes. And that's kind of the main goal of the shard store in the S3 as a system, because shard store is actually responsible for storing data on disks. So to talk about this, we need to talk about write path, which basically includes 3 steps. First, writing chunk data to extend, and then updating index entry, and then updating metadata of LSM to do this, to point to the new index data. Those 3 operations kind of presented as a dependency graph internally, well, at least in the model. And the IO scheduler is responsible for persisting those dependencies in the correct order, which is basically the lower ones and then the ones depend on that. So like the dependencies only persisted if the previous dependency is already persisted. So in the paper, they present this picture of the dependency graph of 3 boot operations. So on the bottom of the picture, there are writes to the chunks. so shard data written to the chunk, and then on top of those operations which depend on the writes, which is index update, and then the LSM metadata update. And like, as you can see from the picture, some of those like got merged together. So there's like one LSM tree metadata update for several puts, even though like obviously chunk data, they have more chunk data updates internally. So, and the whole complexity of IO scheduler and providing correctness guarantees come from kind of that correctly persisting this dependency graph. So for validating that, they're looking for two properties, basically persistence. If dependency is persistent, one of those like rectangles is persisted, it should be visible after the crash. So if it's persisted basically. And the forward progress basically says like, if we do proper non-crash shutdown, in this case, every operation dependency must be persisted. So basically operation succeeded, and we should see all of the dependency persisted and the actual result of the operation. So these are like the properties they check in the system in the presence of crashes. So for that, they need to extend the property-based reference model. The way they do it, the reference model and the test themselves, is basically adding new operations to the alphabet of the operations available for property-based tests, things like dirty reboot, index flush. So basically, because it's again sequential model and the test runner, or the test itself, controls every operation, you can execute those new operations and like emulate things happening. So like after doing certain things, you do reboot or index flush, and then see how model it corresponds to the actual implementation. They also tried to do more fine-grained crashes, like the block level, so not at like index level or like coarse-grained things. But the outcome was that they didn't uncover any new bugs, and because the state space is vastly larger, it just way slower. So this is not the default for how they run tests, because it just was not beneficial. For concurrent executions, so basically we covered sequential execution with crashes. The third lens, the way they look at durability, is the checking concurrent executions with no crashes. So there are no crashes in this. And the main property they check here for is linearizability. And they use actual model checking here, apart from all the previous approaches, which used property-based testing. This is more towards the actual formal verification of the system. And for that, they use like two model checkers, the Loom, the one, as I understand, was already present. So it's like some model checker from a Rust ecosystem, and the Shuttle model checker with probabilistic algorithms, the one they implemented, I assume specifically for that work. So they're like handwritten harnesses to validate key properties as like linearizability and durability, I guess. Maybe just linearizability because there are no crashes. And again, like because Loom is slower but provides soundness guarantees, but the Shuttle is faster but does not provide such a guarantee, they kind of both together provide the soundness scalability trade-off. So like you can validate the shorter histories in Loom, making sure that they're correct and sound. But like at the larger scale with more iterations, longer histories, you have to do like a Shuttle model checker, which does not provide a full guarantee, but still explores the state space. This, as far as I understand. So other properties they looked at in the system, which are also desirable, is absence of undefined behavior. For that, there is a Rust ecosystem tools like Mirror Interpreter and some other Rust compiler dynamic tools, which basically help to avoid undefined behavior in the Rust code. The other thing is serialization they looked at, because like this thing talks to network and serializes stuff. So one of the things they used is a Crux symbolic execution engine, which, as far as instance, is also part of the Rust ecosystem. And that helps to prove panic freedom of serialization code. But on top of that, they also used fuzzing extensively to kind of like the way fuzzing works with serialization code, to make sure that like there are no crashes or undesirable behaviors and stuff like that. So what are the overall lessons from that work and experience? So they mentioned that the development of the reference model took roughly two people for 9 months, and those were formal method experts, so people who like experts in specific area of formal methods. And later in the kind of lifetime of the system, at the time of the publication of the paper, non-experts, but I assume that these are still experts in a shard store, but not formal method experts, contributed roughly 18% of the model code. So like there was some handing over support of the model for sure from experts to the actual development team. Benefits they cite are like early detection. They mentioned several bugs, at least one or two, basically discovered even before code review. So before anyone looked at the code, people were running tests locally and discovered certain bugs. And the continuous integration validation system. So like, because the model runs in the tests and also used in a mock, in mocks and other tests, it kind of helps to keep it up to date with regards to API and some kind of fine-grained details, because if they diverge, you basically see it through tests if you run them continuously, and that's also a great benefit. And the model is executable, so it's not like a model in some different code. They both, the reference model and the implementation are both in Rust, so like I presume they like live together somewhere in the source code. There are some certainly limitations to this approach. So like there are some issues with like evaluating the coverage for property-based tests. For example, they mentioned that one of the bugs they missed but should have found with this approach is the bug where basically system does not hit the internal cache, because I presume the data set of the test was small relative to the cache size, and the basically cache hit rate was always 100%, but the bug was hidden somewhere where you don't hit the cache, and they fine-tune it with the bias, changing the cache size to kind of uncover more, or like to make sure that in the future they uncover bugs in there. There's also some kind of code which I think fair to call accidental complexity of gluing shard store with S3. So they mentioned like routing and like parsing S3 messages itself, and that's like pretty big chunk as far as I understand. And that's not covered because it does not contribute to like durability and consistency properties they were looking specifically for. So that's kind of like outside of that, but still important in actual production system. And the API surface of shard store is actually larger than they cover in the tests, because there are like certain APIs provided for control plane or which are not covered for whatever reason in the reference model. So like not even like all of the APIs are covered. Yeah, with this, I have like a shameless plug. If you're interested in testing things like that, distributed systems and like storage systems, I have a list of the things different companies do, and there's like papers, blog posts, videos. It's there, pretty comprehensive. And that's the end of the talk.